everyone. Good morning, good afternoon, and good evening. Welcome to today's first day, the playoffs. So my name is Thomas Baskoro from the ITU. I would like to welcome you all to this first day, and let's see what colleagues, participants have organized for us. This is the 3 days filled with fun, interesting presentation from teams that submitted solutions for these problems, for several problem statements in this challenge. So to kick off, I would like to welcome Reinhard to give some opening remarks. So Reinhard, good afternoon and welcome to the session today. The floor is yours.
All right, thanks very much, Thomas. Welcome everyone to what we call this time the playoffs. So the best teams of all the competitions are assembled today, and today is the event, the most important event. And then the best teams of today will be presented at the Grand Challenge finale, like our Oscar ceremony, which will take place on the 14th of December. So 23 teams made it to the playoffs, and they will be presenting over the next 3 days. I would say a big thank you, not just to the teams. I would also like to give a big thank you to the judges who are going to listen and evaluate your presentations. We have 13 judges, so a big thank you to all of you for dedicating your time to the challenge. And I would also give a big thank you to our sponsors. We have ZTE as a sponsor of the challenge, and we have the Ministry of Science and ICT of the Republic of Korea, who's a sponsor. So this is the third time that we are running this. It's the third year we are running the competition, and we're happy to have again good presentations, good solutions being submitted to you, which we will, I think Thomas will point this out later, we will also start a special issue of our ITU journal again, which would also be the third time that we're doing this, in our peer-reviewed ITU journal for future and evolving networks. And I would also like to say a thank you to our challenge management board. We have an entire governance structure set up to run these challenges, and it's the hosts, which are some of the hosts which are part of the challenge management board, and individuals who are dedicating their time. So again, a big thank you to the participants who submitted solutions, to the hosts who submitted the problem statements, because that's actually an awful lot of work, coming up with the problem statements and finding the right data to do that. Then our judges, our sponsors, and then of course my colleagues. So Thomas is one of them. Mia is another one, Vishnu is yet another one, and there are quite a number of elves working in the background to make this all work. So big thank you to all of you. And with that, I'll hand back to you, Thomas, and good luck to everyone.
Thanks a lot, Reinhard, for the opening remarks. So I'm sharing the program, as you can see on your screen. We have quite just a sudden change today on the program. One team couldn't make it. So instead of 4 teams presenting in the first session, we are going to have 3 teams. And the first problem statement, this is just a random order, not because they are the first, but just random order. The first problem statement to be discussed or to be presented in today's session is the Graph Networking Challenge 2022. So in this problem statement, it's all about improving network digital twins through data-centric AI. And as we have already pointed out, I've shared through emails to the team's exit survey. Everyone, please make sure that you have filled in the survey, whether you have submitted a solution this year or not. We would like to hear from you and learn from your experiences so that we can improve our competitions. At the same time, we are also going to launch a new special issue on the journal, ITU journal on future and evolving technologies. All teams or all participants who submitted the solutions, please convert your reports into papers that can be published. These are going to be peer reviewed. So please make sure that you convert your reports and submit them for the ITU journal. So with these remarks, I would like to welcome the first team. We have the team Snow All from Canada. Do we have, yes, it's Junior, right?
Yes, it's Junior.
Okay, good morning.
Good morning, Thomas. Good morning, everyone.
Welcome to the session today, and the floor is yours. We have the judges here, so they will be evaluating the presentations from all the teams. So good luck, and we are looking forward to your presentation.
Okay, thank you. So may I share my screen?
Yes, please.
It seems like I don't have the right. Okay, so please could you confirm if you can see my screen?
Yes, we can see your screen, and you can get
started.
started.
Perfect. So I can start. Good morning or good afternoon, good evening, everyone. My name is Junior Momoziazet. I'm a PhD student in computer science at Concordia University in Montreal, Canada. And today I'll be presenting our solution for the graph neural networking challenge. So I will start with some motivations. Deep learning models are traditionally designed along the model-centric approach, where given a data set, the focus is on the design of the learning model. However, creating appropriate data is often the biggest challenge for developing and deploying AI. For instance, in the networking domain, there is no public work showing how to generate or how to prepare good data set. So this challenge comes as a great opportunity to explore the data-centric approach in the networking domain, where we will try to work on designing techniques in order to generate a high-quality data set for the networking domain. So let's understanding through our problem statement. In contrast to traditional machine learning, where we have as input a data set and the task is to train a model or to generate a model, here in our problem statement, we have as input the model, and what we want to do is to be able to generate a data set. So the model that we have is called in this problem statement RouteNet Fermi, which is a state-of-the-art graph neural network model for performance evaluation in the networking domain. And this model has been shown to be very, very good in this task. And the data set that we will generate, we have as input the network topology, traffic matrix configuration, and queue scheduling policy at the level of the node, traffic matrices, routing policy, and the output will be the pair flow delay. The data set that we will generate will be subject to some constraints. Here, I will just talk about the main important one. We want to have a data set of maximum of 100 samples, so a very limited data set. And samples must be from network of up to 10 nodes. So we train a data set, we generate a data set with some limited samples of up to 10 nodes, and we want to be able to generalize to a larger network of up to 300 nodes. So the solution that we propose in this challenge is what we call here a three-step process, where initially we try to make some statistic of the validation set in order to understand some feature that might be good to generate the data set. So first, we generate a first data set that we consider as a basis, where we try to match the validation set. And second, we went inside the data set and see if we can update some parameters in order to cover different or possible use cases, like, for example, different link level conjunction, different traffic flow distribution, different network topology, so that we will have a data set that is diverse enough. And finally, we also try to see if we can clean the data set to keep only high quality data. So in the next slide, I will explain all these steps in detail. Let's start with the first one of initial data set generation. So in this slide, for example, we see some statistics that we extracted from the validation set in order to understand the validation set. We have some flow level statistics, some link level statistics, and some node level statistics. And from this statistic, we made some hypotheses on how we think some parameters in the validation set was generated. So for example, in the different tables here, we are seeing, for example, for the first line of the table that the buffer scheduling policy 54SPWFQDRR was randomly selected. The buffer size was also randomly selected in the list, and so on. And so we identified some parameters that were invariable to the size of the network. So for example, the buffer size, the weight associated to the policies, the traffic flow, packet size distribution, time distribution, type of service. Those parameters were invariable to the size of the network. So if we change the size of the network, those parameters was chosen like in the same way. So we then said, okay, what if we generate the first data set with only 10 nodes where we can also keep those parameters and see what we see. So we also identify another parameter, the link capacity, that we said need to really pay attention to, and in the next slide, I will explain why. So by generating the first data set where we are trying to match the validation set, we're able to gain a mean absolute percentage error, which is the metric of the challenge, of 27%. Then we move to the next step of now going inside the data set and see if we can update some parameters to make the data set really diverse enough. So the first thing that we did is looking at the link capacity. So instead of having a list of link capacity and choose different capacity in the list, what we did is have a list of different diverse link congestion level or link utilization. Our link utilization was chosen according to a normal distribution where the mean will be 0.2 or 0.4, 0.6 or 0.8, and the standard deviation is the mean divided by 2. And given now the link level congestion, which is diverse enough, and the traffic flow going through a particular link, we were then able to infer the capacity of the link. Then after that, we look again at the roundnet Fermi to understand a little bit how it works. And we see that the prediction of the delay, that is the output of the roundnet Fermi, is very affected to the capacity because here in the denominator. So we said, okay, if the capacity that we set in the training set is very different from what we see in the validation set, this might be counterproductive. So instead of using directly the capacity deriving from this formula, what we did is that given the set of capacity that we observe in the validation set, we will consider as a capacity of a link the nearest capacity in the validation set that of this capacity that we infer here. And with that, we saw some improvement. The second thing that we did in order to improve again our solution was to look at the network topology. First, we decided to go with only 10 node graphs because with 10 node graphs, we are sure the number of flows that we have per sample will be the maximum as we can have up to 10 nodes. And what we observe is that increasing the number of network topology is not necessarily beneficial because it might add some variability. So what I mean is, having 100 topology, 100 samples and 100 total different network topology is not necessarily beneficial. So from some experiment, we found that 10 was a good trade-off for our work. And then the question was, okay, how to carefully design 10 graph network? So what we did is looking at the validation set, we decided that we will design some topologies where we have node of degree 1 as we observe in the validation set, and also have a degree distribution diverse enough so that using the shortest path as the routing policy, we can have really different variabilities. And the different parameters like the buffer size, the scheduling policies were chosen according to what we observed in the validation set. The third thing that we did in order to refactor our data set was the flow generation. As of the network topology, we also found that having a lot of flows, different flow distribution, or different flow traffic matrix is not necessarily beneficial. So finding a good trade-off is good. So what we did is we just set 10 different flow distribution or traffic matrices, and then we use these 10 traffic matrices per topology. So first network topology, we generate 10 samples with 10 different traffic matrices, and then second network topology, we repeat again the same process with the same traffic in order really to have something condensed. And we updated also the probability distribution and the packet size of our data set according to what we observed in the validation set. And this is the valuing plot of how our flow looks like in the training set compared to what we have in the validation set. So the other parameters of the flow, like the time distribution, the size distribution, the type of service of the different flow were also chosen according to what we designed and what we observed in the validation set. With these three things that we did in order to cover possible use cases in the validation set, we were able to move from 27% to 8%. Then at this level here, we have 100 samples and the MAPE is 8. We then say, okay, let us look at these 100%, 100 samples and see if some samples may negatively affect the performance of the model. So those samples that may negatively affect the performance of the model, we can consider those samples as noisy. But the definition of noisy sample was not that easy. So what we did here is we look at our understanding of the rounded Fermi and also our understanding of the validation set in order to make some assumption or some hypothesis of what we can consider as noisy. So for example, we said that, okay, as we know the rounded model Fermi predicts as output the average port occupancy before we infer the delay. If in the training set, we have a sample where the average port occupancy is out of the distribution of what we observe in the validation set, we can consider that sample as noisy. So with the first hypothesis, unfortunately, it was not conclusive. So removing those samples didn't really affect on the results. The second hypothesis that we made is, okay, when we look at the average length path in the validation set, it was 4. But we, using the shortest path as routing process, we found that some samples don't have a request of path 4. So we said, okay, if we don't have a path of at least 4, of length at least 4 in a sample, we can consider that sample as noisy because it might be more susceptible to oversmooth. And with that, we were able to identify 10 samples that once we remove those samples to the 100 sample that we had, we saw some improvement. And it comes out that the sample that we removed were from this network topology where we have a maximum shortest path of 3 and a node of degree 6. So with this, then we were able to move from a MAPE of around 8 to a MAPE of around 6. Now, in comparison to the baseline, the organizer of the challenge said that with thousands of samples of network of up to 10 nodes, they were able to get a MAPE of around less than 5. And with our solution, with only 90 samples of network of up to 10, we're able to get a MAPE of around 6. So in conclusion, we have some findings that we think may help the networking community in designing some data set. So first, defining the level of link congestion before we infer the capacity can be beneficial. Having too many network topology is not necessarily beneficial. We can try to find a trade-off and make the network topology to be diverse enough. Having different traffic pattern also is not necessarily beneficial. So still trying to find a trade-off and maybe repeat some sample may be beneficial. And also understanding how the general model works can really help eliminate some negative samples. So in conclusion, we were able to build a high quality data set with only 90 samples of a network to up to 10 nodes. And that can effectively scale to sample of larger network. We have some references here. Thank you, and it will be a great pleasure to answer some questions.
Thank you so much for the presentation. So right now, I would open the floor to the judges. So I see Aber, you open your microphone. So over to you, Aber.
Yeah, thanks, Thomas. Okay, Junior, this is Albert Cabellos. Thank you very much for your presentation. I think it was excellent. Also, you provided a very good context on what was the challenge about and how your solution worked. I think also it's quite impressive, and this does not only apply to you, but to pretty much all the participants, right? Pretty much the model that we provided, Rounded Fermi, is the outcome of the previous year challenges, and it was trained with hundreds of thousands of samples. And you guys managed to get similar accuracy with a few tens of samples, right? And this is quite an achievement on the data-centric AI front, and I believe quite important for the industry, right? Having to train a model with 10 samples, it's tens of samples. It's way easier to generate tens of samples from a network than hundreds of thousands.
Yes.
I have a couple of questions. So the first one is, on the first step, you generate a training set based on certain parameters, and then basically you refine this initial training step. How did you choose the initial parameters? I believe that you have some tables on your slides.
Yes, exactly. So the first parameter that we choose them from the validation set or from our hypothesis that we made from the validation set. So initially what we did is by looking at the validation set and all the statistics, we were able to infer some ways of, okay, if we want to generate this validation set, how do we think this validation set was generated? And this table kind of summarizes a little bit our understanding. So for example, we were saying from our observation of the validation set that the scheduling policy was generated in this list and randomly. The buffer size was generated in this list and randomly and so on. So following exactly the same process that from our observation we observed from the validation set, we set the list of buffer size to be this, the weight that we have for the WFQ scheduling policy or GR to be this, the link capacity to be this, and using those probabilities here, we then randomly generated the first data set.
Okay, thank you. So this, I understand it was manually selected, those parameters, by looking at the validation data set.
Validation set, yes.
Okay, and then my last question is, that's a difficult question, okay? So, but let me still ask it, right? So okay. The challenge, the spirit of the challenge is, okay, how do we need to generate training data sets from networks to train models, okay? So if I have a network in production and I need to generate a training data set from that production network, of course, I want to generate as few sample points as possible because it will be quite disruptive, right? To generate those data points.
Yes.
What knowledge do you think that we can convey to this field after, based on your solution?
What I think we can convey is a little bit what I said in the conclusion. So it's important first to understand the data set that we have, like in the real world. For here, we assume the data set that we will see in the real world is what we observe in the validation set. And once you understand how the data set kind of behave by extracting some statistics, then now you can refine the initial data set that you create in order to consider different possible use cases that we can have by now trying to see what are the parameters that affect the most the output of the model, because it's good to have a good understanding of the data, but also it's very important to understand how the model that you want to train also works. For example, in our case, we identified that this link capacity is very crucial to the network. If we don't design the link capacity in a good way, we might not be able to get the type of result we want. So first, understand the data set. Second, understand the model. And now try to see what are the parameters of the data set that has the most impact on the model. How can you treat those parameters in order to cover different cases, and how can you make your data set a little bit more diverse? So this is what we tried to do in this. And I think if we translate this idea to other data sets, we might still be able to generate good data sets.
Okay, thank you. Thank you so much, Junior, for your answers and for your presentation. And congratulations again.
Thank you too.
Thank you so much. Any other judges with questions?
Hello.
Hi, Evren.
Hi. This is Evren.
Hi.
Firstly, thanks for this nice study. I mean, data-centric AI is really gathering a huge interest. So, as I understood from your paper also, I found your results very useful. But I have a question. Actually, what kind of techniques did you use to tune your hyperparameters? I mean, you are using a neural network. For example, suppose that you did not generate a new data set, you are using the original one, but the hyperparameters that you will use will be specific to the old one. But when you generate a new data set, you should tune your hyperparameters. So what kind of techniques did you use to handle this challenge?
Sorry, I will maybe reformulate the question to make sure I understand. When you are talking about hyperparameters, is it the hyperparameters of the model? So the general model?
Yes, exactly. The architecture and the corresponding hyperparameters, like maybe the hidden units number or learning rate, etc., something like that.
Okay, actually, this was one of the constraints set by the organizers of the competition. So we don't have the right to touch the model. So all the upper parameters has been set as constant, and what we can do is only to change the data set. So we don't have access to the parameter. We don't have access even to the learning to the number of epoch, because we made some update in our data set and we found that the learning was really good, but as the number of epoch was set to 20, we needed more than 20 epoch in order to get good result, but with only 20, we were not able. So we didn't have access to the tweak or the modification of the hyperparameters in the challenge. That was one of the constraints set by the organizers of the challenge.
Okay, thank you.
All right.
Hello, may I ask a question?
Hi, yeah, last one.
Okay. So thank you very much for this great presentation. Just as you were presenting your ideas, an alternative solution came to my mind. I want to have your thoughts on this, how this would work. So my understanding is that you're going to start from a larger data set and reduce it to a smaller data set such that the training performance stays the same. Am I correct?
Start with a larger data set in terms of number of samples, yes, but the training data set will be small enough, and also in one sample, the network topology will be small enough. So in the validation set, network topology start from 15 nodes to 300 nodes, but in the training set, we cannot exceed 10 nodes. So we have like two constraints, as I said here. So first, we cannot exceed 100 samples in terms of larger network. Second, the size of our network, we cannot exceed 10 nodes for the network topology, whereas in the validation set, we have from 50 to 300.
Okay. So it's like reducing the size of the of each input to the model, or is it reducing the size of the data set itself?
Reduce the size of each input and reduce the size of the data set itself. So having samples that are very small and less sample or very limited samples.
Okay, so my suggestion, an alternative solution would be to start from the large data set, do some sort of clustering on it,
yes,
and then take one representative example from each cluster. Did you try this? How this would work? What are your thoughts?
Initially, we tried to do that and use some similarity measure in order to make some comparison, but we were not able to have conclusive results. So we tried different approaches, and this is the approach that finally made us to get the final solution that we proposed today. Yes, but I totally agree. Yes, this also can work.
Okay, thank you very much.
Okay, thank you. We have to cut short the discussion. Thank you so much. If you have questions, everyone, you can type in the chat and Junior will be here to respond. Okay. So now we would like to go to the next team to present. In the program, we have Ghost Ducks. So do we have any representative from Ghost Duck team?
Hi, hello, can you hear me?
Hi, yeah.
All right, so I'll try to share my screen. Can you see my screen?
Yes, please go ahead.
All right, thank you. So my name is Yakov. I will present our solution for the GNN networking competition. This project is work by Eli Sasson, Eli Kravchik, Alexei Gaisinski, and myself, and we are from Togo Networks in Israel. As we saw in the previous presentation, the main motivation for this challenge is building a network digital twin, which can be useful for different analysis of a real network, and in particular to do this with machine learning tools. And as is often the case for many machine learning solutions, we need a good data set to train the machine learning models to solve the task. And in practice, obtaining a good data set from a real network is challenging. Modern networks are very large, so and often you cannot get access to the data due to privacy concerns or due to telemetry costs. And on the other hand, using a simulator is possible venues. There are good simulators out there for networking, but they are rather slow for simulating large networks. And this is exactly the challenge, what the challenge it tries to address. How do we generate a good data set for such networking problems? And our goal in the challenge is to produce a data set, as we saw before. We need to produce a data set to train the RouteNet Fermi model, which is the state-of-the-art model for delay prediction and different other KPI estimations. But in order to address the scale issue, the organizers set a couple of constraints. So the first one is about which networks we can use as in our training data set. So the limitation is we can use networks that only have up to 10 node topologies. While the testing data is a much larger scale. So in the validation set and in the test set, we have up to 300 nodes, which is an order of magnitude larger networks. And the second limitation is that we can only use 100 samples for training, which means that the typical, usually when you're dealing with deep learning models, we need very, very large data sets. And here it's the opposite. We need to produce a very, very small limited data set for training. Okay, so there are different parameters that we can tweak in the data. Basically, we were given a network simulator that we can use to generate data. And here you can see different parameters that we can play with. They generate small graphs of 10 nodes, while the validation set is much, much different in terms of its distributions. So how do we approach this? And we came up with something we call the Oracle approach. What we mean by Oracle is basically the same RouteNet Fermi model, but it is trained without the dataset budget limitation. In fact, during the challenge, we generated pretty much constantly data samples of 10 nodes or less, such that they fit the challenge constraint. And we got a pretty large pool of samples. And we train on this pool a RouteNet Fermi model. We train it to completion on the whole set. So basically, we have a good trained model on the data. And hopefully, we will use it to help us with selecting those 100 samples that we will later use for rapid training of RouteNet. So basically, we first generated the pool, then we trained a couple of Oracle models, and we used them in both for the clustering and selection of data sets, and also to improve our data generation method. So first, I will talk about the data generation method. Once we trained a couple of models on the data that we generated, we saw that there are samples in the validation set which are consistently hard to train on, to basically to get a good prediction on. We see this using the loss plot. So basically, we we see that on those same samples, different models consistently perform bad. They give high loss, while on the others, the loss is pretty low. And in fact, you can trace this to the distribution of data in those samples. You can see that for the hard samples in the validation set, we have higher link loads, higher delays, and larger packet drops. While in the easy samples, the delays are minimal, packet drops are minimal as well, and the link loads are far from being links are being far from being fully utilized. So we were trying to improve our data generation process such that it covers more of these hard examples. Our data distribution generation happened in several steps. So we initially we generated the data in fully random fashion, and we trained an Oracle model. We reached around 7 mean average percentage error. The next step, we generated some additional data where we had matched the distribution of packet sizes and link capacity values and other values inside the other parameters of the data generation, such as they matched those in the validation set distribution. And this way we got improvement in our Oracle model, but we then wanted to improve it some more because we know that from the challenge organizers, you can get to a even lower result in terms of loss. So we generated hard data samples. Basically, we generated data by matching the link capacity so that it matches the traffic demand in the generated networks. And this gave us much higher samples, harder samples. And our final Oracle model got to 5.89 error, which we then used for the sample selection. So once you have an Oracle model and there is already generated the data pool, how do you select 100 samples? And we thought of many different approaches. We tried some of them, or maybe most of these listed here. In the end, the one that worked best for us was the clustering solution. So we cluster the generated samples using embeddings, using vector representations that we generate for using the Oracle model, and then we select from each of the clusters. So how do we create the embeddings? So every sample is a different communication network. They are quite heterogeneous. They have different numbers of nodes and links and flows. So to do this, we take the internal states that we have inside the GNN model, inside the route node. There are three tensors that represent different entities in the communication network. There is path state, link state, and queue state to present these entities. And we pull them using statistical measures like minimum, maximum, and average. And we combine, basically we pull them each of these tensors to a vector and combine the vector to get to a single vector representation. And then all of the samples, both in the validation set and in the training set, have these vector representations that we can use in a clustering solution. So then how do we cluster? We first defined our cluster as being one of the validation samples. There are in total 130 validation samples that we got. And each of them, some of them are hard, some of them are less hard. So we define a cluster around each of them, and we assign to these clusters all of the data samples in our pool. Once this is done, we select from the clusters some top 5 or top 3 items from every cluster, and we get a very small pool. So initially we generated in total throughout the challenge around 270,000 samples of small networks. Now we limited this to a small pool of 500, which are very important, and we use those 500 to further select samples of 100 and train on those samples. And then we thought, how can we improve this further? So And we used intuition that we saw that when we have different Oracle models and they behave in different way on the validation samples. On some of them, they behave better, and some of them they behave worse. And if you choose a different model, the behavior is different also. So one hard sample may be not as hard for a different Oracle. So in the end, we ended up combining the clustering from 2 oracles. And this gave us the best solution. So this is not exactly model averaging, but this is very close. We combined a solution from 2 oracles, and the next step is exactly the same, only that our small pool contains better examples, more useful for training. In the end, so this is the results. You can see on the left table that some results we got internally. So if you just take our large data pool and sample randomly sets of 100, you will get 8.56 MAPE result. If you try to just select the hard data sets from inside just manually, you get a better result, but it's still not as good as you can get. And using the clustering approach, and in particular using the 2 oracles, you can get, we got 6.31 MAPE, which is the best submission that we submitted to the challenge. And in the end, you can see we got to second place, which is very close to the first one. So I think it's quite good. One more thing, after the challenge had completed, we wanted to improve our solution. We thought how we can do this. So, and we focused on 2 things. So first of all, we can improve our embedding by using more sophisticated features. So we added some more quantile information to the embedding pooling, and we got better results for all the method that we tried. And in addition, we wanted to alleviate a little bit the need for a large training cycle at the beginning to train the Oracle model. And we saw that if we apply this clustering solution that we have seen previously, we can apply it on a partially trained Oracle model, and to get a pool of 6,500 samples. And using this smaller pool, we can train another Oracle model that is much better. And in fact, the training will be much faster. And we think we can further improve on this solution given time, of course. Okay, so thank you very much. Thank you for the organizers, and I'm glad to take any questions.
Thank you so much for the presentation. So now I open the floor to the judges. Abe, you have opened your mic.
Yeah, thanks, Thomas. Jacob, congratulations again for your participation and for the also outstanding performance that you achieved on the challenge. I have a few questions. Just one small clarification. When you build the embedding to do the clustering, how do you actually build the embedding?
Yes, I will show it. So inside RouteNet, there are 3 internal tensors, which is part of the RouteNet algorithm. They are basically, as you input to the RouteNet a given sample, a given network, those 3 tensors are created using the trained algorithm. And from using these 3 tensors, also the RouteNet output is generated. So RouteNet generates a delay estimation using these 3 tensors. So what we did is we modified the RouteNet code a little bit so that in addition to its output, its regular output, it will also return these 3 tensors. And then, so 2 of them are 2-dimensional, 1 of them is 3-dimensional. So the 2-dimensional vectors we pool using, we basically take 3 statistics: minimum, maximum, and average, and mean. and we basically average all across all of the Qs, all of the Q representations in this tensor, and we get a single vector of size 32. And the same thing we do for links, and the same thing we do for the path state. Only path state is three-dimensional because it contains a representation for a flow, basically for a route, for a flow. It has a representation for every step in the path. So first we average across the flow, and then we do the same minimum maximum mean aggregation to get a single vector. And then we concatenate the three of them, and we get a vector. And you can do this for, because it averages across the dimension of the entities, you can do this regardless of how many entities you have. So you can do this for the validation samples that have 300 nodes, and you can do this for the training samples that have 10 nodes.
Okay, thank you so much. I find this particularly interesting, right? Because I believe that this embedding might be useful for many other applications beyond data-centric AI, for instance, for optimization and so on, because actually you're clustering an information that can be relevant for this kind of a scenario. So this is quite inspiring. So, okay, yeah. And then my last question is the same to the first participant is, and I believe that you already answered, but if you can elaborate a little bit further. So the spirit of the challenge is to generate as few data points as possible to train a model, right? Because generating data points on a production network is quite disruptive. And I believe that you started with 270K samples that with your Oracle and the clustering, with the clustering, you reduce it. And then you have go beyond that by using a partially trained Oracle with only 6,000 samples, right? If you can elaborate a little bit further into that.
Yes. So first of all, just to emphasize, we did not start with 270 samples. This accumulated during the process, but all of these techniques you can do even with less. So if you have good information on what kind of data statistic you want to generate, you can immediately start generating good samples and apply the clustering solution. In our case, so at the end of the challenge, we had a large pool of samples, but what we did here is we wanted to get to an Oracle model as quickly as possible. So how to do this? So we start to train an Oracle on the full sample, on the full pool, but we stop it very early because we basically saw that it gets to a good enough result even after about I think 40 or 50,000 samples that it has seen in our pool. And this model then you can use for training another Oracle using the clustering. And I think the interesting point here is that when we generated the data, we did not know initially, at least, what kind of distribution we will find in the validation set. So we began with entirely random samples, and we refined a little bit the distribution, but still, if you just sample uniformly from our data pool, you might not get the desired distributions that you want for matching exactly the validation set or the test set, because maybe there is different distributions there. So the idea of using the clustering, because our clustering is based on the validation samples, it helps us focus this second pool, this refined pool of samples. It helps us to focus it on the important distributions. I hope it answers.
I understand. Thank you so much, Jacob. And congratulations again.
Okay. Thank you.
Matt, do you have a question?
Yes. So my question is, thank you for the presentation. My question is, by reducing the number of training samples and keeping the neural network the same, do we not have an overfitting concerned because this approach to me looks like we try to reverse engineer the evaluation data sets. And yes, actually the neural network may be only memorizing the features of the evaluation data set. We may actually be trading the training complexity with generalizability of the model. Do you have any comments on that?
I agree with you that this is a concern. We cannot generate, because of the constraints of the challenge, we cannot generate data samples that are quite like in the validation distribution. Our data is much smaller, so it is not an exact fit.
But still, the generalizability issue may exist, right?
Yeah, the generalization issue might exist. On the other hand, I mean, we do not have any other way of kind of evaluating what kind of data we need. In the end, every solution will be based in some way, well, maybe not exactly tuned, but biased to the validation data.
Okay, thank you.
Okay, thank you very much. And if you have comments or questions, please ask in the chat, and then we can get responses from Yakov in the chat. Now we are going to go into the next next presentation. So we have a presentation from TeamNet. This is Max, I believe is on the call.
Yes, I'm here.
Hi, Max. You can share the screen.
Yes, give me 1 second. Do I have permission to share?
Yes, you should have.
Can you see it?
Yes, please go ahead.
Cool. Okay, so this work has been a cooperation between Benedikt Jäger and myself from the Technical University of Munich in Germany. And since the two previous teams already showed the motivation and the problem statement, I'll just jump right into our approach. So this is the complete overview of our approach. We have in total 3 stages that we go through. So the first one is the generation of initial data sets. For that, we use different random beta distributions for each of the parameters that we can set. From that, we generate a data set of 100 networks, perform training, and get a validation accuracy as a result. And so we repeat this initial dataset generation n times and use those generated models as input for our next stage, which is the individual sample ranking. So we do this for all the networks that we generated in the first step. And what we do is we take a single dataset of 100 networks, which is S, and generate from this 100 new datasets, which each contain 99 networks, removing each sample exactly once from the datasets. And then for those 100 networks, we perform the training again, and again obtain a validation accuracy. And this validation accuracy is then used to determine the importance of the different samples that have been removed. And we use this as input for our third stage, which is the sample selection, where we generate a ranking of the single samples and combine the top ranked samples into our final dataset that we use for submission. Now let's go into the details of the different stages. So first we have these parameters that we can set. A few of them we set to a fixed value. So the number of network nodes, we chose 10 as the largest allowed number for all the networks. And furthermore, we generated 100 graphs with 100 different traffic matrices for each of the networks. Those are the fixed parameters that we have. And then the remaining parameters we took from the validation data set. And for example, for the node parameters, we didn't look at the single parameters separately, so buffer size, scheduler, type of service, and so on, but we only took combinations of all of those parameters that also existed in the training in the validation data set. And then we generate, for each of those parameters, we generate a random beta distribution. And so basically with a beta distribution, you can generate any distribution that you want by varying two parameters, alpha and beta. We can see this here. So y-axis varies the alpha parameter, x-axis the beta parameter. And as we can see, we get kind of here at the top, we get a two-tailed distribution. Then we get a uniform distribution, we can get a normal distribution, and we can get kind of those long-tailed distributions. And then we use one of those beta distributions for each parameter. And for example, or why we want to do this first, so we want to generate a data set that is as diverse as possible. And we want to cover any edge cases that can occur if, for example, the packet size is very skewed towards one value. And an example, if we look at, for example, the node degree that we want to determine, let's say we have 4 possibilities for that, and using different beta distributions here with different parameters, we generate a weight for each of those node degrees. And then we pick with those weights from those node degrees. And so basically those weights are the pseudo probabilities for the associated parameter values. And we use this first step to generate n datasets. And we select the best evaluated m training datasets for the next step. The next step is then the sample ranking. So we want to basically determine the impact that a single network has on the whole dataset accuracy. So this can be positive or negative impact. And we do that by removing one sample from the dataset and then compare the accuracy of this 99 sample network to the 100 sample baseline dataset accuracy. And if we get a worse accuracy, that indicates the sample has a higher impact. And as an example, let's say we have our 100 sample dataset, which gets a validation accuracy of 8.5. Then our first 99 sample set, from which we removed sample 0, gets a validation accuracy of 8.7, which means the impact of the sample can be characterized as 0.2. And let's say for another sample, 54, we get a validation accuracy of 9.5, which gives us an impact for this sample of 1.0, meaning sample 54 is preferred in our case. And we use this approach to create a ranking of all the samples and use that again as input for the next step. And the next step is the recombination, where we select the 100 best ranked samples, including some random variations, and combine them into our new dataset. And this will be the submission dataset. We repeated this step a couple of times, got different results. And for our best submission, we had a combination of 2 datasets that have been generated using this beta distribution approach. The dataset S1 has had a validation accuracy locally of 7.3, and S2 had a validation accuracy of 7.6. And after the ranking and recombination step, the final dataset that we submitted had locally a validation accuracy of 6.9, and the final submission accuracy that we got was 9.8. And for this final dataset that we used, here are all the topologies, just to be complete. As we can see, we have some topologies that look quite similar or are isomorphous. But overall, we had a quite diverse set of different topologies. And finally, a list of all the submissions that we had, with our third place submission at 9.7. And that is everything from me. Are there any questions?
Thank you so much for your presentation. And we are open for questions. So I see a bear. You can go first.
Yeah, thank you, Thomas. Hi, Max. So congratulations again for your participation and your placement on the challenge and the performance that you achieved. So I have a few questions on the process. So if you can go back to slide number 6, I believe. Yes. So here, when you say sample, that's a single sample, or by sample, you mean 100 data points from the data set that you generated with a beta distribution?
No, this is a single network.
Okay, so it's a single data point inside one of the 100 data sets that you generate.
Yes.
Okay, and then how do you measure the impact of the sample, the 0.2, 1.0 that you put? So how to obtain those numbers, the validation and the impact?
Mm-hmm. So we basically train the 100 sample dataset for 20 epochs and take the lowest accuracy. And we train the 99 sample method, the 99 sample dataset, train it for 20 epochs, take the lowest accuracy, and then compare this accuracy to the baseline accuracy.
Okay, I see.
And how we score it is basically, so we use the relative error, but it's basically, it doesn't matter since we just want to rank them.
Okay, I see. And then in the recombination step, do you take basically well, you have already your ranking, right? And you take the top 100 samples.
Yes, so that was the idea. In the end, we included some randomness to that because it got better results, and we suspected that it's because we kind of just in the ranking step, we just compare it to the baseline accuracy, which might be overall the baseline accuracy might be worse, and so it might be easier to improve on a worse accuracy, and so we had some additional randomness here. So, but the idea is to take the top 100, yeah.
Okay, and then I have my last question. So again, right? So the spirit of the challenge is to generate as few data points as possible in a production network to be able to train a model, because generating data points in a production network is disruptive. So what is the knowledge that your solution provides into this, let's say, more into this challenge? Not, I'm not speaking about the performance, right? But
yeah. So basically, our idea is that starting from our final resulting data set that we submitted, we can basically go back propagation style to the original parameters of the beta distribution that we used to generate samples, and take those. So basically, if we have a way to synthetically generate data sets like we've had a chance in this challenge, we can get this final result, go back to the beta distribution, and then use it as input for a real data set generation.
Okay. Thank you, Max, and congratulations again.
Thanks.
Okay, so it's time to get back from the break. Welcome back, everyone. And I'd like to inform our teams that are presenting in this session that please make sure that your GitHub repositories are set to public and not private, because if they are you set them to private, then the judges will not be able to access your reports or your slides for evaluation. So just please take note of that and make sure that your GitHub repos are public. Now we are going into the second session, or the last part after the break. For all judges, I've shared the evaluation form. Please make sure that you have access to the evaluation form for the part 2. If you don't, just send me a text message, or you can send me a chat on Zoom. I will share the information with you. Now we are going to the first part. We are going to handle the network failure prediction on CNF 5GC with Linux eBPF. And we have the first team, which is the Big Fools. I will stop sharing the screen. I don't know if Emmanuel is here.
Hello.
Yeah, please share your screen.
Okay. Yeah, I think now my screen is shared.
Yeah, go ahead.
Hi, my name is Emmanuel Pascal, and I'm from Malawi, which is in Africa. I'm here representing the Big Fools team, and I'm only the team member. Today, I'm going to talk about network failure prediction. So we are going to start with the introduction. Then we are going to dive deep into problem statement and data extraction. After that, we are going to take a quick look on proposed machine learning models. Then we are going to see the results. Then we are going to end this presentation with the conclusion. So a lot of companies around the world, they have deployed 5G network. And sometimes there might be interruptions in this network for a few seconds up to a lot of hours. And this is what is called the service outage. So the company must act before there is a service outage. If they fail to act, there are some other problems which may come along. For example, the businesses which depends on the network make losses due to the loss of connection. Secondly, the company itself, it may make losses as the customers switch to new service providers. Lastly, the company loses its reputation, preventing it from growing. So if we use machine learning, the network failure will occur so that the company can prevent these problems. So we can use the data of how the packets are being transferred to the network to make these predictions. So the problem statement requires us to predict when the network failure will occur as early as possible and with the highest accuracy. That is, the F1 score was supposed to be greater than 0.9. So the problem was divided into 2 tasks, which were similar. For first task, we have to use all the metrics, and also the metrics, I'm just trying to mean the columns which were provided. For second task, we have to select the columns and make our prediction. The target variable was the number of user equipment registration failure at 10 minutes. So each data set comes with multiple test cycles or test scenarios. We can see that, and this is an example of a test scenario. So for first 90 seconds, it is a preparation phase where there was no any event occurring. For the remaining 90 seconds, it was registration and the registration phase. This is where we pick only one example from each test scenario and combine them. The table below shows the summary of selected examples. Here I have a graph of target variable against detection time. The red line indicates the abnormal data or where the network failure occurs, while the green line indicates the normal data or when the network failure did not occur. You can see that the abnormal data is nonlinear, while the normal data is linear. And also you can observe that below 70 seconds, the normal and abnormal data, they have intermingled. This flow chart is just a summary of main points on this slide. So you can see that we combine the selected rows, creating a new data set, and we use that to train the task 1 or task 2, or train our model or get the predictions. So there were some other things which were supposed to be done in order to complete task 2. Before we get the prediction, we have to select the columns or the matrix. So the metrics were selected based on their importance, or that is their contribution to final F1 score. So the bar graph below just indicates some of the contributions of some features to the final F1 score. If the target variable is greater than a certain value, let's say V1, the network failure was occurring. And if it was less than the same value, the network failure did not occur. And that value was called the threshold value. So the models, the problem is treated as supervised machine learning type, and regression models and decision trees were used. As we have already seen on the first graph, that the target variable was composed of continuous values. The following models performance were compared. We have support vector regression, Bayesian ridge, gradient boosting regressor, extreme gradient boosting regressor, and the random forest regressor. So some improvements were made in order to improve models performance. SPR kernel was changed from radio passive function to sigmoid, as the sigmoid function can work better with nonlinear data and also linear data. And our data set was the mixture of linear and nonlinear. SPR regression parameter C was changed from 1 to 0.095, as this solves a fitting problem. So we are going to look at the results. Here I have the performance for different models, and this is a group bar chart. The groups were formed based on the time in seconds and the number of figures which were used. You can see that in all three groups, SPR model is getting an F1 score of greater than 0.9, while the remaining bars are getting better as we move to the right groups. If we move to the right, this table is the data which was used to plot the first group. So for task 1 results, you can see that using the detection time of 10 seconds, we can have an F1 score greater than 0.9. Okay, this is a graph for different models. You can see that all the graphs are going up and down below 70 seconds. This is because the normal data and abnormal data have intermingled before we reach 70 seconds. We can generalize that the SPR model have better performance compared to other models in general. So here I have confusion matrix. So we have a lot of true positives compared to false negatives for task 1 at 10 seconds. And this confusion matrix, I'm just using SPR model. The second confusion matrix at 70 seconds, as we can see at 7 seconds, our F1 score is 1.0. So as expected, we only have true positives and false negatives. So for task 2 results, if we use a single filter and detection time of 64 seconds, we can get an F1 score of greater than 0.9. If we increase number of figures, the detection time has to reduce in order to get a similar F1 score of greater than 0.9. This is the relationship between the number of figures and detection time. You can see that the relationship is not linear. There are some other features which affect more the detection time compared to other features. So removing this feature is affecting more detection time compared to removing the other features. So I have here the confusion matrix for SPR model for task 2 at 20 seconds using 527 features. You can see that this confusion matrix is similar to the first confusion matrix, as we have a lot of true positives compared to false negatives. So we had a presentation area, and this is the performance comparing the Big Foot performance with the other teams. So during that time, the big schools will get a detection time of 10 seconds and an F1 score which was greater than 0.9, while other team it was 3 times to 5 times that value. In conclusion, network failure can be detected with F1 score greater than 0.9. Reducing number of features generally increases detection time. SDR, XGPR, and Bayesian reach were some of the models used. Thank you. Dickfus Emmanuel Basco.
Okay, thank you for the presentation. I'd like to ask the judges if you have questions to this presentation. Hi, Tian. Good morning.
Morning. Hi. I have a quick question. So thanks for the good presentation. So can you go to the slide with the title data set for task 2?
This one?
The data set for task 2. So maybe before. Okay. Before space. It's the one just before part 3 proposed the machine learning models, the one before that. Okay, this one. So my question is here, at the bottom, you have a bar chart listing top 10 of most important features. So my question is, how did you use the F1 score to compute the feature importance?
Okay, I use the XGP classifier. So XGP classifier has a function which can calculate the feature importance or the contribution to final F1 score of each feature.
Okay, so the point is like so when you use the so can I say the SG what?
XGPR classifier.
Okay, so and then you use the some some function inside the library to get the feature importance, like the weight of the feature. Yeah. Okay, I got that. Thank you.
Thank you.
You're welcome.
Yeah, judges, if you have questions or comments.
Hi, this is Umut. I have a question again, the same about the feature importance. I'm curious, like if you have only used, I mean, to select the features, if you have only used the feature importance of the XGB, or like for each model, you also evaluated the feature importance for the corresponding model. So, like, did you do like, for instance, you train the model, specific model for, let's say, SVM, and then which include all the features, and then evaluated the feature importance and just selected like top whatever 10 here, I guess. Is that the case, or like?
I only use XGPR, and when I get the figures, I never change it. That like I have only one place where I calculate the feature importance.
I see.
I only calculate once for all models.
I see. Okay, thanks.
Okay, if we have other judges, so we can open the floor to anyone else on the call who has a question or comments. Any questions from the floor? If no questions, or if you have questions later on, you can put them in the chat window, and I believe Emmanuel will answer you later on during the session. Okay, so now we are going to go into the next presentation. Next up is in the same category of the problem statement, network failure prediction, and we have the team MLab NFP. Gion, good evening.
Yes. Good evening.
Hi, the floor is yours. Please, you can share the screen.
Can you see
Yes,
the slide?
please go ahead.
Okay. This is Yuan Lee, and I'm a member of MLab NFP from the University of Tokyo. I will present on regression-based practical network failure prediction on 5G core network using AutoML. To begin with, I will start by briefly introducing the background of this challenge. In this challenge, we aim to predict the number of registration failure at 10 minutes early and accurately. There are two different tasks. In task 1, we use all metrics for prediction, and in task 2, we select a part of metrics for the same prediction. The dataset provided for this challenge is in 10 seconds interval, and there are 70 rows per cycle. In addition, the failure event starts at 1.5 minutes. From now on, I will introduce what our team had worked on and the results of each task. First, let me begin with explaining about the basic concepts of our work. We thought that it is not appropriate to make predictions at a specific time because if the failure event starts afterwards or if the predictive value exceeds the threshold afterwards, the failure cannot be predicted. So in our work, instead of judging by looking at a specific time, we monitored the entire cycle to see if the failure could be predicted as early as possible. Also, we aim to provide a method that can apply failure prediction for all data by time up to 600 seconds. Here, the most ideal situation for early prediction is when the prediction value of abnormal cycles exceed the threshold as early as possible, and the prediction values of normal cycles do not exceed the threshold before 600 seconds. This is a quick summary of our method. I will continue by explaining about our method, starting from the model. The model that we use is called AutoGluon Tabular, which is an open source AutoML framework. As shown in the right image, AutoGluon assembles multiple models and stack them in multiple layers. It is capable of taking unprocessed raw data and making high-quality predictions. In this challenge, we use regression model of AutoGluon, and these are the submodels selected automatically. For training data tuning, we took different strategies for normal and abnormal cycles. We downsampled the whole cycle by selecting 6 rows at 100 seconds interval. By doing this, we reduced the cycles that exceed the threshold after the prediction time. In addition, we tried to avoid a data imbalance by taking the same number of rows for both normal and abnormal cycles. For abnormal cycles, we selected 6 rows from the early stage of failure event, trying to achieve early prediction. For the output data, the number of registration failure at 10 minutes for each cycle was used. By doing this, we let the model predict the number of registration failure at any time in the cycle. For selecting the threshold, we used the prediction of the training data set. We separated the prediction value to normal and abnormal cycles and selected the threshold by taking the mean value of the 99th percentile of normal cycles and the 1st percentile of abnormal cycles. In this task, the threshold was set to 25.66. This is a summary of the results in task 1. We succeeded in predicting at 120 seconds with the F1 score 0.904. Apart from this, we also calculated the F1 score at different time up to 600 seconds in order to check whether the prediction is applied for all data. Here, the F1 score was 0.904, so we were able to confirm that the F1 score is constantly over 0.9. This slide shows the result in more detail. These histograms show the row index of the predictive values exceeding the threshold for the first time in each cycle, and the cycle that does not exceed the threshold until 600 seconds is set to -1. In the left histogram, we can see that most normal cycles do not exceed the threshold until 600 seconds. In the right histogram, we can check that most failure cycles exceed the threshold before 120 seconds, resulting in high F1 score. Next, I will continue by explaining task 2. In task 2, in order to select the metrics, we use random forest feature importance of task 1 model. Due to the limitation of computation resource, we calculated feature importance by randomly selecting 400 rows maintaining 3-to-1 ratio of normal and abnormal cycles. We calculated feature importance twice, and both results are shown as tables. Here we found that TCP/RTT of UDM and container memory RSS of C-Advisor are the important features of prediction. So we selected 86 columns of UDM TCP/RTT and 10 columns of C-Advisor container memory RSS, resulting in using 96 columns in total. This is our thesis on UDM TCP/RTT and container memory RSS being the important features for failure prediction. UDM is the network function that conducts subscriber management and user authentication processing. Thus, we thought that UDM is highly related to registration, which is the target in this challenge. Also, since RTT depends on the processing time and the container memory RSS is the amount of physical memory consumed, it can be thought that they both increase when failure occurs. In task 2, we worked on it twice, and I will start by briefly introducing our first try. In our first try, we basically used the same strategies with task 1, but in threshold tuning, as you can see in the middle histogram, there were a lot of low values observed in abnormal cycles. So we decided to see only the early stage of failure events and used 5% outliers for threshold tuning. As a result of our first try on task 2, the prediction rate of abnormal cycles was high, as you can see in the right histogram. However, there were a lot of false alarms and normal cycles, resulting in low FN score. But here we were able to find out that UDM TCP/RTT and C-Advisor container memory RSS has potential in predicting abnormal cycles, and that improvement in prediction of normal cycles is needed. So we changed some of our methods and carried out task 2 once more. First, we separated the training data by 500:100 ratio and created validation data. Here we used the former for training data tuning and the latter for threshold tuning. In training data tuning, we downsampled the dataset by selecting 12 rows in 50 seconds interval for normal cycles and selecting early 12 rows for abnormal cycles. By increasing the number of rows per cycle, we improve the prediction on normal cycles. For threshold tuning, we used the validation dataset with 100 cycles and set the prediction time to 130 seconds. This is because when we checked the FN score at 120 seconds, we found that it is below 0.9 throughout the cycle. So for selecting the threshold, we changed the threshold from 20 to 60 and checked the FN score at 130 seconds and 600 seconds. The crossing point of the FN score was about 40, so we set the threshold to 40.00. This is a quick summary of the results on task 2. We selected 96 features and were able to predict failure at 130 seconds. The FN score at 130 seconds was 0.907, and the FN score at 600 seconds was 0.955. The histograms and confusion matrix show the result in more detail. In the left histogram, we can see that most normal cycles do not exceed the threshold up to 600 seconds. And in the right histogram, we can check that most abnormal cycles exceed the threshold before 130 seconds, resulting in high FN score. Lastly, these are the quick summary of the results and methods of task 1 and task 2. Thank you for listening.
Thank you very much for the presentation. Now I would like to open the floor to the judges for questions. Judges, please, the floor is yours. Hi, Tian.
Hi, it's me again. Hi, thanks for the good presentation. I just have a quick question about the data set. So did you use some open source data set or you collected from some simulations?
Can I ask you once more? What was the question?
Okay, so
I think I can maybe respond to this question in this case.
Yes.
So the data set was provided from testbed by a network provider. So they have a testbed, a 5G core network testbed.
Okay, yeah, I got that. Thank you.
Thank you.
Any questions from the judges? So just one question from me. In this case, you did auto glue, and in terms of the machine learning model, did you compare with any other, or because I know AutoML has, when you do AutoML, it produces results for different models and rank them. Did you had some comparison of different models?
Before trying AutoML, AutoGluon, we actually tried like LSTM and other models, but we ended up using AutoGluon because it is like, it has high quality and it actually automatically like selects the best model for the training. So we ended up using AutoGluon.
Okay. Thank you. Questions from the floor? Anyone who has questions? The floor is still open. We can take some questions. If not, then we are going to close this presentation. Thank you so much, John, for the presentation.
Thank you.
Okay, next up, we have one more presentation for this problem statement. And we have Takeru from University of Tokyo. Hi, Takeru, good evening.
Good evening. Can you see it?
Yes, yeah.
Okay. My name is Takeru Haki. My team name is UT Nakaura AI. My presentation title is Network Failure Prediction on CNS 5GC with Linux eBPF. This is the agenda. First, I'll talk about summary. In task 1, my model achieved F1 score equal 0.92 with detection time equal 140 seconds. In task 2, my model successfully reduced the number of features from 3,325 to 329. My best solution resulted in 329 features. Detection time equals 140 seconds. F1 score equals 0.97. Next, I'll talk about introduction. CNF, which containerises network functions and operates 5G core networks on virtual servers, is an important technology for full-scale 5G operation and realization beyond 5G. Due to its speed of startup and restart, high scalability for easy service expansion, and rapid service deployment. Currently, many carriers are deploying cloud-native 5G core networks. As advocated by the Ministry of Internal Affairs and Communications, autonomy and reliability are among the functions required for beyond 5G. 5G core networks in beyond 5G must have systems that constantly monitor the network, automatically detect failures based on log data, and automatically recover before users are affected. Metrics that can be obtained from containers include CPU utilization, memory utilization, file system, and network usage of the container. However, this metrics is not enough to predict failures in advance, so lower layer information is needed. Therefore, by utilizing eBPF, one of Linux functions, we can obtain lower layer detailed data from the virtual server on which the network is running. By using this data, we will attempt to detect failures at an earlier stage. Next, I'll talk about dataset description. This explanation is the same as that of the previously presented teams, and it is therefore omitted. Task 1 aims at area failure detection. Create a model to predict the number of UE registration failures at 600 seconds from the sum point T. The objective of task 1 is to make the value of T as small as possible within the range where the F1 score exceeds 0.9. This section describes the method used to solve task 1. We chose deep learning with 2 layers of LSTM as a model. The model that uses all features is called all model. And the model that uses all features except those that are 0 for all periods in the training data is called removed data, a removed model. The number of features is 3,325 for the old model, and 1,723 for the removed model. We scaled both training and test data from 0 to 1 using the minimum and maximum values for each metrics in the training data. The threshold was defined as 0.3. This was because the minimum number of UE registration failures at 600 seconds in the test data was close to 0.3. This table shows the experimental detection time. Time steps is the input sequence size. Delay is the interval between input and output. Data size is the number of data used for training. Lost input is the number of failure data included in input when predicting at 600 seconds. The result was followed. This figure shows the F1 score for each model. The blue line indicates the old model, the green line indicates the removed model, and the red line indicates an F1 score of 0.9. The old model achieves an F1 score of 0.91 with a detection time 150 seconds. The removed model achieves an F1 score of 0.92 with a detection time 114 seconds. The removed model is able to predict area and more accurately than the old model. I found that the removed model has higher performance than the old model. This section describes task 2. Task 2 aims reduce metrics. By using eBPF, over 3,000 metrics can be retrieved. However, the overhead of capturing and storing all of this amount of metrics is significant. So the goal is to reduce the number of metrics as much as possible. In task 2, I created 2 models. First model is the difference from normal model. The upper figure illustrates the metrics employed for 11 cycles. The range with blue background is the range where the failure is occurring. This shows that the metrics behaves differently in the blue range. Only metrics for which the absolute value of the average of the metrics at the time of the failure was greater than twice the absolute value of the average of the metrics at the time of normal were employed. This process reduced the feature size 3,325, sorry, 25 to 329. Second model is a feature importance model. Feature importance was calculated using a random forest, and the features with high importance were used for LSTM training. In the feature importance model, I experimented with detection time equal 140 seconds and the feature size of 1,723, 1,500, 1,500, 400, 329. I compared the difference from normal model and the removed model. The F1 score for the difference from normal model was 0.97 with detection time 140 seconds. The difference from normal model has higher performance than the removed model. The difference from normal model with 3,000 features reduced has the best performance. I compared the difference from normal model and the feature importance model. The difference from normal model has better performance than the feature importance model under the same condition. The differencing process was shown to be effective. This section describes the analysis of features. Right figure illustrates the top feature importance levels calculated by random forest. According to random forest, TCP metrics are important in loss failure. The left figure shows the difference from normal model specific metrics. I found count metrics are important in loss failure. This section describes conclusion. The difference from normal model is the best solution. The difference from normal model was successfully predicted with a detection time of 140 seconds and an F1 score of 0.97. I improved model performance by reducing the number of features. Finally, feature works. Since this failure scenario was a single scenario with only packet loss, we would like to make predictions for other failure scenarios such as CPU overload. We would also like to make predictions for different user traffic characteristics such as watching video on YouTube, surfing the internet. We would like to analyze factors and metrics as we can hypothesize that the important metrics would differ depending on many factors such as failure scenarios, traffic characteristics, and network size. Ultimately, we would like to analyze the changed or retrained in practical use. Thank you for listening.
Thank you so much for the presentation. Right now, I'd like to open the floor to the judges if you have questions or comments to this presentation. Comments or questions from judges? If not, I'll open the floor to all participants. If there is anyone with a question, please, you can raise your hand, open your mic, and you can speak.
Hi, Thomas. I have a short question.
Yes, please go ahead.
Thank you. Hello, thank you for your presentations and your good results. I have a short question. So you choose the model for the text one, use LSTM. Can you explain why you use LSTM and you didn't use other method?
I don't experiment other model.
Sorry?
Oh, I don't experimented other model, only LSTM.
Yeah, so you choose only LSTM. Did you try the other model to achieve for better results or not?
Not.
Okay.
Okay, thank you. Hi, Tian.
Hi, sorry, it's me again. So I just thanks for the good presentation, but I just have a quick question about the removed model has high performance. Can you please go to that slide? You are
sorry, I cannot hear. Removed model?
I think you went one slide with the title, a removed model has high performance. It should be slide 11. the next one.
Slide 11. Next, okay.
Yeah. So here you just mentioned here you see on the second line you say successful prediction at detection time 140 seconds by removing zero metrics. So did you have you ever tried to figure out why it worked or why it's better when you remove the zero metrics? I'm curious about that.
Oh, your question. Why the removed model, removed zero metrics is a better performance?
Oh, yes. Or you just tried and you figured them. Sorry to interrupt you.
I think zero metrics is all period zero. So a normal and abnormal period is to zero. So it's have noise. So when all metrics use model performance is become low. So remove zero metrics, removing the noise. So remove the model is higher performance, I think.
Okay, thank you. Thank you.
Okay, thank you so much. Thank you for the presentation. And now we are going into the next part of our session. Just a reminder, judges, you can, if you haven't been scoring the teams, you can score all the teams now. But if you have scored, that's okay, that's fine. Now we are going into the second or last session for today. In this session, we are going to discuss on multimodal beam prediction challenge 2022 towards generalization. We have 3 presentations. I like to check, is Max, are you here?
Yes.
Hi, Max. Good afternoon. Okay, so the floor is yours, so you can share your presentation and you can start presenting.
Okay, thank you very much. You can see my screen, I guess, I hope.
Yes.
Okay, perfect. Thank you. Okay, thank you very much. I'm going to present BeamBench. As the title says, it's a benchmarking framework which I mostly written to compare different techniques for this, let's say, highly interesting topic. And I want, as the subtitle, as understanding line of sight requirement, I will explain in the next slide what does this mean. So let's go to the beam prediction task in general. So in high frequencies, above 6 gigahertz, you have a certain beam characteristics of your base station. And since we have a lot of antennas needed to get a high directivity because of the huge path loss to get to the UE, therefore, we need a lot of antennas, and therefore, normally you have a certain amount of code books. Code books means you form a beam in a certain angular direction, for example, here. And now you can choose for different codebook entries, you can choose different angles for this. So the task was to use multimodal, as there are multiple different sensors at the base station, for example, a camera, a LiDAR, a radar, and effectively the GPS position of the UE. And the task was to find the best beam for this currently specific time instance. So there was a time sequence of 5 snapshots, and the task was to predict from the first till the last, at the last sequence instance, the best beam. And therefore, one uses a DBA score, a density-based accuracy metric. And the metric has the notion that if you have a certain, let's say, angular space, so here's the angle, and then you have a beam power over it, that not only one beam or one codebook gives you reasonable power, but multiple, and therefore you have some scaling towards to say, okay, I'm also fine with a certain distance between those two. So this is what the DBA score means. The DBA score is normalized from 0 to 1, meaning 1, I get a perfect hit in this uncertainty, and 0, I'm completely off. But what is really the challenge here? The challenge is finding the target in my sensor, then estimating which path towards the target is the best one, and then choosing the codebook which shoots the most energy into this path. So there's two different notions here. Let's say if you would have a normal base station where you have only line of sight, then you have your target, which is a badly drawn car here. And then the best beam, if nothing is there in the world, there's free space, then the best beam would be always looking directly onto the car, meaning the task will be predicting the angle of this car within my local coordinate system. So now this would be one idea. So this would be a classical approach. The other approach would be saying, okay, is there a reflection in my scenery? Can I use this? And gives this a better codebook. This depends if you have, let's say, for example, blocking, what this distractor will tell you. If the bus drives in front, then you will get a distractor, and then it might be going over reflection. Will you give a better beam? So these are the two notions. The line of sight path will be always, let's say, the fallback solution. And I want to see what does AI/ML bring here. Because if you have only the line of sight notion, then you could use the GPS position to estimate the angle. And this we're going to see now. So it's effectively a multi-stage problem. You need to detect in your sensor where's the car, estimate angles of the best power, and then use the codebook for this. So let's say, what is the challenge here? If you now look at the cars in the three different sample scenarios. So we have effectively 4 scenarios, all are differently placed of the base station. Some are similar, but from the test, this is from the test data set, and this is from the train data set, we can see that even the car type, the car color looks different in a new scenario. You can always see the GPS antenna here. And the field of view is also different. Meaning now you need to find a machine learning approach or an AI approach which can work with all of these kinds of changes within different settings. So the task was to predict, training on those scenarios, predicting this scenario. So the first thing is you see that there's distribution shifts, and now the first thing is you want to calibrate your data. The data was provided by DeepSense. Thank you very much for this. So this is the guys from Arizona State University. And therefore I had to do a calibration. So at the beginning, I calibrated the GPS in the sense of I looked at where the car is in the middle of my camera, and then I calibrated the GPS saying this is my center point of my beam. I will skip this because I don't have that much of time, but let me show you why it is good to use an AI/ML approach. So if you now have a baseline, which should be classical, because I always want to see, does it make sense to use something more sophisticated than the classical approach? So the idea is, how does the angles and the beam index, for example, in my scenario, correlate together? So these are the angles for the scenario 34. And there you see, okay, are the angles in degree measured from my GPS positions. And if you now look at the beam index I normalize it from 0 to 64 beam index, you see that the color is matching quite nicely. So there is still the notion that in a dominant line of sight case, let's say this scenario, which was actually the most line of sight case, this traditional GPS to angle to beam index matches quite well. And therefore I built from scratch quickly a least square solution and found out that there's a very nice, let's say, connections between the angle and the beam index, and you get an overall result of 0.64 with this. So now I know what I have to beat. this I need to beat with any ML technique, else I could just stop. So this is the thing we need to know. So therefore, I created the framework BeamBench, which uses different modalities, different techniques, all of them joined together, going down in a more complex way, saying I can use the camera image, I can use some form of autoencoders, going down into the latent space, and then join them in a fusion neural network. I can use the radar, LiDAR, GPS as much as one, and with the 0 and 1 switches, I can toggle off any, let's say, feature together. So I can say, okay, my neural network, let's say, giving you an example, should use the camera image completely. I say, okay, this is my one. It shouldn't use the feature encoding. And I want to use radar as well. Then I can just turn this off, and the other things I don't want to use. And therefore I can say, okay, this quickly in the configuration, test it out. By the way, all of the neural networks are optimized using neural network intelligence, which is a Microsoft open source tool, which is an AutoML tool, which uses hyperparameter space and Bayesian optimization, which allows me to optimize each configuration for itself so that I'm confident that I'm getting the best results for this configuration as much as I can. All of them configurations are mostly CNNs because they are most likely image-based tasks. The alternative, which was coded up, was the sequence approach. The sequence approach was using LSTMs. Sadly, from the training data set and the test data set, the time sampling was different, meaning my LSTM systems didn't work, and I shouldn't have gone with better, let's say, transformers or something like this, but I didn't have time anymore to do this correctly. So most of the best results I get are the direct approach, and there's always a room for improvement now. So let me show you what is the overall idea here from the results. Is now you have the scenario 31, which is your test scenario. Then you have the scenario 32 till 34, and you have some certain CDFs. The CDF is, let's say, from 0 till 100%. And the DBA score. And then how do you read such a plot? For example, for scenario 32, I get an average, a DBA score of 0.7 on, sorry, on my classical solution. I can see that all of my neural network solutions are better in scenario 32 and 33, and in 34, it's not like this perfectly, but these are all the machine learning approaches I did. For nomenclature, it is GPS dense, meaning I'm using the GPS modality and going down for dense neural network to the beam index. In the camera, I use a CNN. What does adapt mean? Adapt is there was an adaptation data set given to us. So I use this as well and see if this makes a difference, which will be shown in the test data set as well. And then you see a more complex combination, which is effectively LiDAR autoencoder plus camera autoencoder plus radar contrastive learning, and then GPS data as a regularization term, and then the adaptation version of this. And this is a middle way where you have a camera autoencoder plus the GPS, and then you adapt to this new data set. Effectively, what I can show you is that all of these machine learning approaches, if I trained on the data set or adapt on the data set, it didn't make that huge of a difference, which is great, meaning I already have a good solution. If it's not seen data, which is on the adaptation data set, I'm getting a good result out of the box, or the similar solution. For the scenario 31, which was completely unseen beforehand, I don't get these results. So I see that I'm better with more complex solutions, but I'm not as close as the classical solution. Therefore, I take the few samples to move this curve very close to the classical solution. And one note here is that the classical solution is very close to the line of sight approach and the machine learning approach, as this was a dominant line of sight case. So if it was more non-line of sight, this curve would be way here. So effectively, what I can show is that I can take with few samples, I can adapt to this. It's not perfect generalization, like drop it and then it works. You need a few samples to adapt. The overall results, so I just picked out some of them, not all of them, are summarized in this table. And effectively, as you remember, we had this to beat the 0.641 in overall score. So these are all the test scores. I can see that if I use a more, let's say, advanced camera autoencoder with a regularization term of GPS or something like this, then I get a nice evenly distributed performance, meaning I don't favor any scenario directly. I don't, let's say, hugely different between those two, and I get an overall good generalization approach. Obviously, you're always looking to get something like same performance over the whole scenarios. If you want to have a perfect score, you would have gone for, let's say, more dominant training on a specific scenario and therefore boosting these scores up. Okay, so effectively what I can say is that I'm beating the classical solution by at least a little bit. That is good enough to give a reasonable generalization idea. So there's a lot of improvement you can still do here. Thank you very much, and I take any questions.
Thanks so much, Max. Judges, I open the floor for questions and comments. Hi, Koichi, good evening.
Okay, thank you for the presentation. Maybe I missed your explanation, but could you please go back to page 6? Yeah, thank you. So what's the difference between these scenarios, 4 scenarios?
Thank you. So there is this, let's say, there was given 4 different, let's say, measurement deployments. So the base station was put at one street here, which goes in this direction, and then there was an intersection. The base station was placed here, so we're always looking currently on the configuration, and now you have a different configuration here. And the scenario 32, 33, and 34 are those 2 here, plus another one, which I just put, didn't have the space to, which you have for training. And the scenario 31 is the one which you don't have for training, and this is this one. So they are, you want to see how you can work training on something completely different street, completely different car. You see, this is my target and this is my other target now, and how you can still detect this car in the new scenario without or with limited data sets.
Okay, I see. Thank you. So you mean that in the slide 6, you also mentioned that there are no real generalization. So yeah. your method is a little bit maybe not so adaptive to the older scenarios. So do you have any idea how you can make it more generalized?
Let's say you have different stages of generalization. So a generalization stage, which you say you need a little bit of samples to work. This is what I can show. If you need, you don't need to retrain from scratch. You're getting direct out of the box okay performance. You see it that in the 50th percentile, I get around a 0.5 dBA score, but I'm not getting deployed without any samples. I'm perfect. What you need to change to go for a full generalization step, I think Arizona won't like it, is more data. You need more scenarios, more diversity, not different cars, different types. You need to find ways, maybe data augmentation to make it more diverse. 4 scenarios are not enough. If you look at ImageNet in YOLO or whatever, you have so many different configurations. Then you have a chance to go to generalization.
Okay, thank you.
Hi, Madi. Over to you.
Yes, thank you very much, Maximilian. My question is, did you see any difference between the performance with camera images in the day and night? Or did you do any precautions to treat differently between day and night samples?
I didn't want to, okay, good questions. I didn't want to, let's say, okay, this is night and I want to enhance it with some image filtering or something like this. I didn't want to, because I wanted to work out of the box in a generalized way. And not optimize any scenario, saying, okay, this is the day, this is the little bit offset or something like this. So I didn't want to change this. So, but what I see here is, if you're looking into this table, you see scenario 32 and scenario 33. These are similar scenarios. So the base station was not exactly on the same position, but they're very close, and they were day and night data sets. And if you take a look, the day data set is way better than the night data set. So there is a degradation based on camera in night. So yeah, there is a difference.
Okay, thank you.
Thank you. Do we have judges, or do we have any colleague on the call who would like to ask some questions?
Hi.
Hi, Tian, yes.
Hi, thank you for your excellent presentation. So I want to ask, in the overall results on page 7, the GPS, they are direct. What does direct mean?
I can use the GPS in the raw format without calibration. And this would be direct meaning. So this would be longitudinal and latitudinal. What I did for the other ones, the classical ones, is I converted in X-Y coordinates and then into range angle. And this was a pre-processing step. And this was very helpful.
Okay, thank you.
Any other questions? Maybe just a quick one from me. In terms of the GPS pre-processing, if you consider the other scenarios where you have more fusion, and if you add pre-processing for the GPS, would you get better results, or be not much improvement?
You get better results, yes, but not that much of an improvement.
And in the case of pre-processing, for example, on scenario, let's say 32, you talked about the difference between scenario 32 and 33.
Yes.
And if you would, let's say, maybe add further processing on that scenario, data set from that scenario, do you think it would improve on the performance, or maybe just add overhead to the complexity?
I personally think if you would, let's say, if you would want to make this a practical system and you go ahead and deploy this in the field, I would personally say, okay, what are my regions of interest of the code book, for example, and then I would, let's say, process the camera in such of a masking, saying, okay, this is clear sky. I don't need to look at clear sky. These are buildings, just cancel them out with some filtering. So you can make improvements for specific scenario, but they will be always, let's say, I have this notion, where does my UE doesn't go? I am deployed on a data set. So I would do it, but the task was generalization.
Thank you very much. I think now we can go to the next presentation. So thanks a lot, Max, for the presentation. Right now, we are going to go to this second presenter in this problem statement. We have Team TII. Hi, Kim. Good evening.
Good evening. Good morning. Good afternoon. So
the floor is yours.
Yeah. Okay. I'm sharing my screen. Hope you can see it.
Yes. Okay. I think you can make it full screen.
Okay.
Yeah. Yeah.
Okay.
Good.
Thank you. Hello, everyone. Hello, judges, audiences. We are from researchers from TII, and we're presenting our solution to this sensing and beam prediction. So first, we will briefly introduce you to the problem, and then we go for our data pre-processing methods and analyzing methods, and present you the deep learning solution, give you some experimental results, and making conclusions. So briefly introduce our understanding and analysis of the problem. So basically, the target is to, in a scenario when we go communication beyond 5G, and especially in high frequency millimeter wave scenarios, and with a massive antenna with narrow beams. So it can theoretically boost our capacity, improve our performances, but we have challenges in the mobility beam management, especially the high frequency have high propagation loss, and for the vehicle users, for example, in high speed, it also require high reliability. So in this case, that the traditional beam management based on like SRP, SINR is insufficient in solving this issue. Sensing and communication has been arising quite well in the 6G. And so the task here itself is that can we use sensing multimodality sensors to predict the best beams to help the beam management, beam switching, or even further power allocation, etc. So in this specific task, as we see, we have the data from the camera, LiDAR, radar, and the GPS. We have multiple sequences, that 5 sequences of the sensors and 2 sequence instance of the user's GPS location. And to predict the beam with the maximum blink receive power measured at the base stations. And what GPS informations, theoretically, if you are in a line of sight, of course, the GPS, if you get the angle correctly, then you can almost get the beams. But GPS always, you will have a higher latency to get it. If, for example, the UE to report the GPS location to the base station, it consumes you the power to measure always the GPS, and also you may have interruptions. So it's not always reliable in the practice. And if you're in a non-live sites, especially you have blockage, then it will not be effective. And also in a scenario, if we have like the reflections or from the other buildings, and also in some cases that if GPS is not effective, then we believe that sensor information could help. So this is the objective of this task. The challenging includes that we have the data sets from 4 scenarios, as we know that each scenario collected with different time, location, and on a sampling rate. So for example, we have one scenario in the morning, in the day, and one scenario in the night. This will have high effect to this, especially for the images. And the target is that we train on 3 scenarios, then we need to generalize our model to test our model performance on another scenario with a very few data. So the challenge also increases because we have multiple sensors. How can we fuse the data from different sensors? But the goal is to how we effectively use them. For example, the images, camera images and the LiDAR, it's a very complex information. There's all the backgrounds of static and mobile objects. There's no labeling of them. It's hard to detect, say, which one that the object is the user. And also there's a misalignment between the camera, LiDAR, and the GPS. So how can we effectively use information? The goal is that we, based on this DBA, distance-based accuracy score of the top 3 beams, basically it's computed as the distance to ground truth. It makes sense because if you're closer to the ground truth, you have higher probability that you get the connection better. So basically, in this case, that when a night is one hot, if not the best beam, but if adjacent beams, then you're still able to be well served. So from our solutions developments, we're first looking into the data. We're thinking of that how can we use the image data better. As we explained, there are many of the objects. It's hard to recognize which one is the best user. So we first try some enhancing techniques. For example, we try if it's a nice scenario, can we use something some tools that we can enhancing the brightness to allow the model to better recognizing what's the objects. Or we tried the semantic segmentation, which that so we try to labeling these colors that inside the images based, and then brightening that and make the background darker. We also try some maskings that we mask the other areas and keeping the rows and keeping the colors. The goal is to guide the deep learning model focus on the region and objects of interest. In fact, when we present the results, we'll see if this is work or it's actually maybe less effective in some cases. And we also experiment trying to develop a method to pre-process the LiDAR data. Basically, first of all, as we say the LiDAR is 3D. How can we use it into together with images or other modality? You can use some complex clustering the points or using some point nets, but this will have very high computation capacity. But in this task, actually, every data we have the area of interest. So what we do is that we explore this bird eye view projection methods. Basically, we did describe the region of interest in grid cells and then encode the high intensity. And so in this case, that as you can see, when we have these 3D point clouds, we project it onto the bird eye views, and we further applying. If you have some complex environments, is it as we are more region of interest into some areas like the cars and the streets, can we filter in them some of the backgrounds that is less useful maybe, and keeping these areas stable? What we do is that we compute the moving average of all the samples, and then we try to find out what is the moving areas, moving objects. We also do this customizing the field of view. As I say, because LiDAR provides that the view is much different of the images. So we try to calibrate the views as here, as the same as where the image has area. So this will actually, it also reduce the complexity, but also making it focusing, preserving this information, but also focusing more the same as the image area. The goal then, this LiDAR point clouds can compensate the images if the images information is less effective. And we also process some of the LiDAR data. What we do is that we try this based on the Fourier transforms from the LiDAR into the range angle and range velocity maps. And then as we see here, this will give us more reliable information, especially there's image and LiDAR information. It can be affected quite significantly by the environment. Also for the GPS, as I say, first we do a min-max normalization because from the coordinates, according to the maximum coordinates of the users, we do normalizing then between the 0 and 1. And then we refer to the base stations GPS get the relative coordinates. And also we do a calibrating the angles because also the central pixel of the image is not always at the 0 degrees of the user's location. And we do the calibration. So this means that once we make sure that once the views, the beam, the 0 beam area is actually pointing directly to the image center. So this will give us better estimation about where the users actually is to mapping the user's location to the image. And so based on from the pre-processing, we develop our deep learning solutions. The deep learning is based on the transformer-based multimodal learning. And so basically what we do is that we utilize this, after this pre-processing, we utilize the ResNet convolutional networks that extracting the high dimensional features from each of the modality. As we have already processed system into the 2Ds, and then the convolutional layers can be applied. And at each of the convolutional outputs of feature maps, and we use a GPT-based transformer. And this will fuse the features from multiple different modalities, and then learn the correlations between them. And we try to make it to learn the abstractions of these raw data, and the abstractions will be propagated to the next convolution layer. And each convolution layer, it learns higher dimensional features, and then in this case, we're expecting that that the model could learn or could compensate how much each of the modality information giving. And also with the GPS, we do after the pre-process, we do this using the raw GPS into the transformer, and hopefully you can get the coordinates that can position where the users is, and together with the lidar speed and angle, that when combining the speed angle together, this can help together with the GPS, then making that better positioning the users and predicting where the users' mobility. And together with the sensory information, that you can predict the environments, and then you can get a better beam prediction results. And the output we use, then we attach the output with the 624 beam index. So this will give final models we will do. And in order to train this model specifically for beam prediction, we develop some of the methods. First of all, because we know our target is not only the best beam, but also how close are we to the best beam. So we soften the beam index from 1 hot to the Gaussian distribution based on how the dBA score was defined. So we match the cost entropy, turn the cost entropy function. For example, if this K is the best beam, so we make a distribution based on the K minus 4 and plus 4 beams, because as with the defining how the dBA score is defined of the maximum of the neighboring 3 beams. And we apply this focal loss because we see that the data has a huge imbalance, and also we try to, if you perform well in scenario, the other scenario, like scenario 31, you have less data. So the focal loss can make it the model. Basically, what it does is focusing on some of the hard examples. For example, if this is the example and some of the areas are already well classified, basically it will make the loss lower, and the loss will be higher on some hard examples that you have high, low confidence areas. So this makes the model to be focusing on some areas that are hard to change. And also we also test some of the data augmentations, like changing the images and also adding some noise and downsampling the LiDAR data to getting some of the more data to solving better the data imbalance in some in the scenario we have less data. And during the training process, we will also apply some others, making the model stable, like the cosine decay of the scheduler. Basically, it will do from a higher learning rate and then make it gradually lower to gradually reduce the gradient descent process, keeping some windows to exploring of the other momentums. And also we use an exponential moving edge basically to make the model more robust, especially for the when you get more fluctuations at the end of the training. This will get an average weights, exponentially average weights of the last steps that to say instead of the instantaneous model. So this we do the experiments, and so first we start with a single time step, which was one instance of the sensor data. Basically, we can see that from the scheme A, we can see that in all these 32 to 34 this training. This scenario has a large data samples. It gets a higher scores, but it performs very poor in these unseen scenarios. And once we try to do a fine tuning on this scenario, so these ones that we improve, but we also get the lower in the others. So which gets to us the improvement scores on here. So we think that, okay, we have putting the multiple sequences and adding some more information to the model. For example, we add the velocities from map from radar. We add the focal loss and the cosine decay learning rate to help to better make the model more robust and solving both of the imbalance data and also we soften the beam index. So in this case that we can, as we this comparison based on the schemes A, we can see that it actually improving here on the 32, 33, and we are achieving similar performance, a little bit higher performance than B, but this case is without any fine tuning on the specific scenario 31. So this gives us a bit more generalization. And then we try to improve it, adding the normalization of GPSs, and we can see, and also adding some augmentations. And this on the 31 scenario, as expected, it improves a little bit. And then we try to apply more of the making model more robust on the exponential moving edge. This we can see improves a lot in especially in these two scenarios and making the overall scores much higher. And finally, we try to apply the calibrating the field of view of the LiDAR as making the same region of interest with the images. This we can see improves a lot in almost all the scenarios and making our best scores as we get. We also test some of the pre-processing techniques as we presenting before. For example, we will try to do the background reduction. We try to filter the LiDARs or masking or doing segmentation on the images. Unfortunately, what we see in here compared with the baseline schemes F, which is the best score we get, you can see both of the image and LiDAR is not working that well. This we can, from this expectation, we think the background information is necessary or important, especially the visual background can be getting you good in some non-life science scenario, and also can better positioning the users and predicting how the user is moving, and how the reflection from the background will be affecting the correlated the users to the position. Also, we apply the EMA so that as we see before, this helps a lot the performances. And in our training, we do see the convergence gets quite good after 60 to 80 epochs on both our training and validation sets and also on different scenarios. So finally, what we learned from these texts. In our contribution, we do develop the transformers deep learning, especially for beam prediction, and we do the pre-processing of this and utilizing all the sequential data from multiple modalities. And we made the model generalized to different scenarios, and the model essentially itself can be used for different applications. So the advantage is that the model, even though the full model is customizable, especially the size can be reduced and the size can be used, and it takes the data sequences and different modalities. This can be also, if you have a less sequence or less data, this model is also useful. And it can be robust in different scenarios, especially when, even though this challenge is a good view and the line of sight, but if you have a not extreme environment with fog or rain, this can still help with different modalities inside the model. And also, if your scenarios not always have the camera LiDAR always, in the network, some users or base station, they have LiDAR, some have radar, some have camera, and this model is still useful that you can fuse all the modalities, or you can use less modality. For example, you can just use LiDAR or GPS, or you just use radar. This is still working quite effectively. And also you can do we do consider enhancement to learning more the sample relationship, make it generalized, do some semi-supervised learning to reduce the label needs. This will making it more useful in the real scenario that in most of the unlabeled scenarios, we can still use that to predict effectively. And learning, doing feature learning, especially GPT model do a little bit of the abstractions, but going further, if when you get the abstractions here, and then it's more essential to the generalization we think. Also, this you can extend this part, the output part, to make it other tasks like the predicting power, etc. And also you can this model you can change each of these inputs and outputs into different like sensing, localization, or even do more trajectory precision. And even this can be used to collaborating controlling the vehicles or robots for multiple sensors. So this is the end of our presentation. Thanks a lot for your listening.
Thank you very much for the presentation. Do we have, maybe first I'll ask the judges if there are questions. Hi, Madi. Go ahead.
Yes, thank you very much for the presentation. To me, your neural network models look very complex. Do you have any measurements in terms of the computational complexity of your solution?
Okay, so in total, the model has millions parameters. When we train the models on the GPUs, it takes around we have around 14 to 50 minutes per epoch, and converges at 80. Even though our original model have more, the reason that this model looks large is basically it fusing all the data and utilizing all the sequences, modality, sensor data inside. But the good thing is that this is more generalizable from different application and tasks. And actually, we also, when we begin with the task, we try to use, we can use less of the image, like images or run radars within the model, and this can be much faster. And also, the applicable, if we think, is that once the model, if you train the model on some of the data, actually some of the, if the users have devices has less of the computing complexity, you can do a fine tuning on some of the data you get, and this actually weights or is also useful for fine tuning and retraining for the devices that it gets the new data.
Okay, and another question is an ablation study. Do you know how much is the contribution of different modalities to your final performance? Which one is playing the most important role?
Okay, so first of all, of course, as we actually, of course, in all these scenario tests, we use OR, but when we at the beginning, we will see adding GPS, so theoretically you can improve, but actually adding images, and actually you can also improve a lot actually, because image and GPS that making in the line of sight scenario that making good results. But in some other scenarios, like in the evenings or these scenarios, we're finding that adding the LiDARs actually is essential. And into radar mostly is the velocity will help a lot. Will help us a lot. So so due to time frequency, of course, we didn't test all the combinations of different things. But as our model is more flexible, we are actually continuing testing all these things, and especially useful for devices with different sensors.
Okay, thank you very much.
Thanks.
Thank you very much. I think now we need to move to the next presentation. So thank you for the presentation. Right now, we are going to the last presentation of this session, last but not least. We have Team MMJ. Junan, are you here?
Hello, can you hear me?
Yes, we can hear you. So yeah, can you stop sharing the screen here? Yes, thank you.
Hello? So
yes.
can you see my?
Yes.
Okay, I will start, and
you can,
I will
thank you.
Okay, I will show you my solution in ITO challenge for a multimodal beam prediction challenge. And actually, this is also part of my master thesis. And I read my master thesis in Institute of Telecommunications in University of Stuttgart. And I'm Junan Wang from Team MMJ. And I will present my solution in following 3 parts. Firstly, is data processing, and then train and optimize model. Finally, its results. In the part of data processing, I focus mainly on position data and camera data. I also check the radar data and the LiDAR data, but they have limited detection distance. And mostly I cannot extract valid data of the experimental car. So I gave up these two using of these two type data. So firstly, it's position data. Left side shows the top views of experimental car tracks in all scenarios. The color bar represents normalized beam and gain. It ranges from 0 to 1. And the base station for scenario 32, 33, and 34 are marked with red, blue, and green points respectively. As can be seen, the experimental car travels on 2 roads that are perpendicular to each other, and each road has 2 lines. And in the right side, it shows the experimental car track in each scenario. In scenario 32 and 33, the experimental car track are very similar. It's a right angle turn. And the scenario 32 collect data mainly from daytime, and scenario 33 collected data from night. And in scenario 34, it contains all possible routes. In scenario 31, the tracks are very simple, exactly 2 straight lines. In order to make the angle calculation close to the field of view, I also make a calibration of position data. Firstly, reset the coordinates to the difference between the experimental car and the base station, so the original point can be considered as the base station. The new coordinates are rotated around the expected angle. Mean position in each scenario is chosen to calculate mean angle, and the coordinates is calibrated with that angle. Left figure shows the original tracks, and the right figure shows the calibrated tracks. Then the range of position data in each scenario can be shown in the table. Overall, the distance ranges from 9,8 meters to 98,5 meters. Angle ranges from minus 56,4 degree to 63,7 degree. Next is camera data, a combination of target detection algorithm ULEVER7 and multi-target tracking algorithm DeepSort is used to process camera data. In order to improve tracking accuracy, some images in each scenario are stitched together in moment order to a long video. And here its left figure shows the detection results of 1 frame. As can be seen here, it's the class car ID and the class car, and the confidence is marked on the top of bounding box. So once the car ID can be filtered out, and we can get corresponding bounding box. Here, angle in position data is used as a basic to filter out the experimental car. So we have to calculate the angle in RGB image. In the right figure, here it's the coordinates of center point of bounding box is calculated. And here X coordinates is chosen to calculate angle in RGB image. And the X coordinates is normalized to a specific range according to the dataset from DeepSense 6G. The field of view, it ranges from minus 55 degree to 55 degree, and then calculate arctangent, and the corresponding angle in RGB image can be calculated. In order to avoid the effect of car size, the left side angle and the right side angle of bounding box are also calculated. The car whose left side angle or right side angle close to the angle in position data is the experimental car. But only some of the position date, only position date of first two samples in a sequence are known. Therefore, only some of the car ID can be filtered out with the position date. So we also need to filter out all car ID. Firstly, tracks in each scenario is plotted in moment order. Here, take scenario 32 as an example. In the figure, blue points represent tracks and the red points are peaks. The interval between two adjacent peaks is considered as a track. Therefore, each track can be determined, and then count all filtered out car ID at X within 35 meters for each track. The most frequent occurrence is recorded as IDR. In each track, reset all IDX to IDR. That means there is only one car ID in one track. Based on IDR, corresponding detection bounding box can be found. And in this way, tracking accuracy is much improved in each scenario, and especially in scenario 31, the experimental car can always be tracked. So finally, the input data is 24-dimensional vector. It contains position sequence and bounding box sequence. The output data is 64-dimensional one-hot encoding based on the beam indice. Once state determined, the next step is to train the model. Here I use a standard neural network to train the model. It contains input layer, hidden layer, and output layer. In the figure, here A represents the activation function. Each hidden layer is followed by an activation function. As output data contains only 0 and 1, so the binary cross entropy is chosen to train the model. For the selection of the number of hidden neurons and the activation function, an automated neural network intelligence is used. And I mainly use the neural architecture search from NNI to find the best model. So as can be seen, the left side shows the model is trained based for the all scenarios, based on the all data set from all three scenarios, scenario 32 to 34. And for a further improvement, I also trained the model for each scenario based on the data set from each scenario. And it needs to be noted that model for scenario 31 is trained based on the dataset from scenario 34 because it contains all possible rules. And here is the results. Firstly, performance in training dataset. There are two criteria, prediction accuracy and the DBA score. Left figure shows the comparison of prediction accuracy for top 5 beams. As can be seen, compared with the model with only position data as input, the model with position data plus bounding box data as input, the prediction accuracy is improved by approximately 2%, and NNI improved the prediction accuracy by a further approximately 5%. And the right figure shows the comparison of DB score for top 3 beams. As can be seen, for the sensor data improved DB score for approximately 0,01, and NNI improved DB score for another approximately 0,01. The DB score for top 3 beams with best model is close to the 0,9. And compared with the original model from base code, as can be seen, the prediction accuracy is improved by approximately 20%. And for the result of scenario 31, as can be seen, prediction accuracy for top 3 beams can be achieved at 52%, and DB score for top 3 beams can be achieved at 0,65. Above are all results for the training dataset, also the validation dataset. And for the result in test dataset is shown in the table, and here is the DB score for top 3 beams in each scenario. And overall, the model for all can achieve DB score for top 3 beams and 0,59, and the model for each scenario can achieve DB score for top 3 beams 0,63 and an improvement of about 0,04. And that's all. Thanks for your attention, and please feel free to ask a question.
Thanks a lot for the presentation. So I open the floor to the judges for questions.
Hello.
Hi, good morning.
Hello.
Everyone, please go ahead. I think you just started asking.
Okay, thank you. Thank you for this nice presentation. I have just one question. Did you mean using specific neural network model for specific scenario, or did you use one model for all scenarios? I just missed it.
I trained both. Firstly, this is the way how I found the best model. And firstly, I trained it based on all the data set, and here is the model for the all data set. And for a further improvement, I also train model for each scenario. It's here. You can regard it as two solutions, maybe.
Okay.
Yeah.
Okay, thank you.
Thank you.
Okay, so
okay, yeah, I'll go ahead. Thanks for the nice presentation, John. So I guess several questions, but first let me start from the endpoint. Do you have any insights into like why your models performed like comparably worse in the test set, like with respect to like validation data set? Like we have this 50% here, right?
You mean the difference between the results for the training data set and the test data set?
Yeah. Like it seems like it did not generalize very well, like because you see the scenario 31 is like 35%, while you have like around 50%. Like, do you have any insights on that?
Yeah, that's a good question. I also think much about this, because when I training the model in training data set, I only have from for example adaptation data set, and in the NI, I always can set an objective for the aim of the training. For example, when I treat model, I say the aim is to maximize the dB score for top 3 beams. But for scenario 31, I only have maybe 50 samples from adaptation dataset. So I train it based on that 50 samples, and then here is the results for the validation for the adaptation dataset. And for the test dataset, there is more data, and its performance not so good. And another possible reason maybe it's for the filter of the bounding box. In the test dataset scenario 31, I can always keep tracking the experimental car, but for the adaptation dataset in scenario 31, it's the 50 samples are not always constant. So I track them in a sequence. The sequence contains the 5 samples. So when I track the sequence, there is always a large error. I cannot so good to track and capture the experimental car in scenario 31. So I thought it's maybe also one of the reasons why it's a difference.
I see. Maybe like the car was different. That maybe have an effect of that. Okay, thanks. Also, like I'm curious about the complexity of your model. Like, is it low or like like what is the number of parameters in your model?
Here.
Like how many like parameters do you have in these layers, for instance? Do you know the number or?
Yeah, in the dense layer, it ranges from 200. In the dense layer, I have for example, candidates, it's from 256 to 2048, I think, yeah, for the dense layer.
I see. Yes. Okay. Okay, yeah, I was just thinking about like scenario 31 has like 50 samples, so yeah, like if I guess some other model can generalize better. So
yeah, I thought of.
Yeah. Okay. Thanks.
Yeah. Thanks.
Thank you. Tian, please.
Hi, Jenna. Thanks for your presentation. I have a question about the like the model you use here. I just noticed that you have like 6 hidden layers for your CNN, actually DNN network. And then I noticed that for the first 5 hidden layers, you actually used some different activation functions. So my question is, how did you determine which activation function to yours, or you just figured out with different experiments and decided with the best performance, or you use some other methodology to determine this?
Yeah, I determine the activation function for each hidden layer with the automated neural network intelligence. Here is a framework ratio, and it has 2 main functions, value choice and layer choice. Value choice is used to find the best, for example, hyperparameters in the model. I use the value choice to find the number of hidden neurons, and I use layer choice to find the corresponding suitable best activation function. So in the value choice, I list some of the activation functions to be candidate, and in each trail, one of the activation function will be chosen to the model, and the network will give an output, and then the top K results will be shown in the end. And at the end, I will take out the first best model and with the corresponding hyperparameter and the activation functions.
Okay, I got that. Thank you.
Thank you.
Hi, Gina. Thank you for your presentation. I want to ask, at the beginning, you mentioned that you utilized YOLO and deep salt to detect the vehicles in the images, right? So
Yes.
you showed the results. I think the image is from scenario 32. So how about the performance in the nighttime scenario 33 and 34? How about the detection performance in these 2 scenarios?
In the results of YOLO version 7 and deep salt, scenario 32 and 33, I think about 80 or 90 experimental car can be tracked, and in scenario 34, it's a little bit lower tracking accuracy compared with the scenario 32 and 33.
So you mean that the performance is also acceptable, even though in the nighttime scenario, right?
Yes, yes.
Okay, thank you so much.